Good morning, students. I am Dr. Monika Khetarpal. I am Associate Professor of Physics in Government Dungar College, Bikaner. I welcome you all in this enlightening session of MSc Previous Physics. I am dealing with the first paper, that is Classical Mechanics. In my today's lecture, we will discuss about principle of least action. For this purpose, I consider a variation of path, and this variation is considered in such a way that initial and final points, they also vary. That means position coordinate vary, and there is also variation in the time. And this variation of time does not mean that there is a variation along the path, but time varies at endpoints, even varies at the endpoints of path. But along with this variation, there is a one restriction, that at endpoints, position coordinates are held fixed, and I am representing this variation by delta. Earlier in Hamilton variational principle, we were discussing the variation which were denoted by a function delta. This delta and del, they are different. We will discuss their difference in further. This del represents the change in position, but in this there is no change in time. I am defining a quantity which is termed as action. It is defined as A equal integral T1 to T2 summation Pj Qj dot dt. This is action A. And from this action, we will derive the principle of least action for a conservative system. The principle of least action for a conservative system is defined as del T1 to T2 summation Pj Qj dot dt. This is equal to 0. This is the principle of least action for a conservative system. Now, I am going to discuss the difference between these two variations. That means the del variation and delta variation. So, first of all, we will be dealing with the del variation. For this purpose, I have taken 2 points, A and B. We have to travel from A to B. That means these are our endpoints. For this purpose, I can walk through any one of these paths. For these different paths, in this variation, we have to take that time of travel from endpoint A to another endpoint B, that must be the same. That means the time factor does not depend on the path which we are choosing. That means we have to speed up or slow up in order to make the total time travel along every path same. And in this variation, that means del variation, time speeds up or slows up, and in this variation, energy may or may not be conserved. That means variation in energy can be possible. That means energy can be conserved or it cannot be conserved. Now, I am moving over to another type of variation, del variation. Here I have drawn a graph between coordinate and time. Time is taken on x-axis and coordinate q is plotted on y-axis. If I am taking a path AB, initial and final endpoints are Q1 and Q2. I can take another path, A dash and B dash. For A to B path, time of travel is T2 minus T1. And for this different path, time of travel can vary. So in Dale variation, time of travel along different paths may be different. Endpoints are the same. Here this path, for this AB path, initial point is Q1, and similarly for A-B path, initial point is Q1. And for this path AB, the final point is Q2, and for the path A-B dash, the final point is again Q2. But we can clearly see from the x-axis on which we have drawn time that time of travel for these two paths is different. So in Dale variation, we have that energy will remain conserved along every path. So the system point may be speeded up or slowed down so that total energy of the system remains constant along actual and varied path. Whereas in the previous case, it was that energy may or may not be conserved. So these are the basic difference between these two type of variation, del and delta variation. Now, from the action A, we will derive the principle of least action. For this purpose, we will define the function, that is, we will define the expression for our function which is delta. As we have different paths, we will label them a parameter alpha. As in Hamilton variational principle, that means in Dale variational principle, we have denoted different paths by same letter alpha. And in Dale variation, we know that T was independent of alpha. Whereas, as I have shown in this graph, that T depends on path. Hence, T will be function of alpha, which are different paths. That means T is a function of alpha. Therefore, the path will be a function of T as well as alpha. That means Qj equal to Qj, functional dependence on T and alpha. So variation del Qj will be expressed as d alpha. Two parameters are there. Variation with respect to first will be del Qj by del alpha plus dqj upon dt, dt upon d alpha. This is dqj upon dt. This is qj dot, and coupling these two terms, del alpha d by d alpha, this is equal to del. So we can express the first term as del qj, and this is qj dot. And since there is a variation of time along with path, d alpha dt by d alpha, this will be del t. Hence, we can represent the parameter del by a function delta plus del t d by dt. So, we have expressed our parameter delta in this form, an important form which we will be using earlier. Now, we are going to prove the principle of least action. For this, I am starting with the action A. Action A is defined as integral T1 to T2 summation j pj qj dot dt. And since we know the relation between Hamiltonian and Lagrangian is h equal to summation pj qj dot minus L. We can obtain the value of summation Pj Qj dot. It will be H plus L. Writing A to be integral, limits are T1 to T2, L plus H dt. Now, since Hamiltonian is conserved, we can take it outside the integral as it is a constant quantity. So this term, second terms, comes out to be H. The limit is T2 to T1. So H T2 minus T1. So del variation will be del A del T1 to T2 L dt plus H del T T1 to T2. Now I am taking L dt, integral L dt to be equal to I. Differentiating this, L will be equal to I dot. Hence, using the first equation, which is del equal to del plus del t d upon dt, I am applying this parameter on my function I. This is the required equation. Now I am putting the value of I. I have assumed I to be integral L dt plus delta. Instead of I have L dt, and del I by del t is expressed as I dot. Del t limits are T1 to T2. Now I am using my second expression and putting this value in my second expression. Del A will be expressed by equation 5. In order to solve the equation 5, I will find the first term of this expression. The first term is variation of integral T1 to T2 L dt. Since Lagrangian depends on generalized coordinate Qj and generalized velocity Qj dot, I can express this term from its partial dependence in two terms. And from Lagrangian equation of motion, I know that d by dt del L by del Qj dot minus del L by del Qj equal to 0. This is the Lagrangian expression. I have d by dt del L by del Qj dot to be del L by del Qj. So putting the value of del L by del Qj as d by dt del L by del Qj dot, I get this expression. And when these two terms they are coupled, they can be written as a single term in the form d by dt del L by del Qj dot del Qj. Now from the operator I have find the value of del Qj to be equal to del Qj plus del T dQj by dt. This is del Qj can be written as del Qj minus del T Qj dot. So I can write my expression as d by dt del L by del Qj dot. Instead of del Qj, I have this expression. So opening the term d by dt, as there is an integral and differential, these both cancel out. So I am left with the term del L by del Qj dot variation Qj minus del L by del Qj dot del T at the endpoints. Now since we know that at endpoints del Qj must be equal to 0. Endpoints are same for all the paths. So this first term will be 0. This term comes out to be equal to minus summation del L by del Qj dot del T. And this del L by del Qj dot, we know that this is equal to generalized momenta Pj. So substituting del L by del Qj dot to be Pj, I get my expression as minus summation j pj qj dot del t. Using this expression in my fifth expression, which was this expression, I have find out the value of this first term. These two terms remaining the same. I have my expression as del A equal to this form. Now I am taking del T is common in these three terms. I have taken it out common. The factors which are in the bracket is h plus L minus summation Pj Qj dot, and the limit is T1 to T2. The relation between h and L is h equal to summation Pj Qj dot minus L. Now we know that action A, delta A is 0. Using this relation, we get delta A to be 0. This is termed as principle of least action. That means delta A, which is summation j pj qd dot dt, this must be equal to 0. So in order to understand this principle, we must know the very difference between these two type of variation, which is very important. As I have already stated, this tail variation involves a change in path for which the time of travel for the different paths must be same, and there must be energy can be changed or it may be constant along different path. Whereas in del variation, time of travel along different paths may be different and energy can be conserved along every path. Thank you students for watching.